All right, we're going to finish off chapter 14 with acid-base titrations. Here we're going to interpret titration curves for strong and weak acid-base systems, compute sample pH at important stages of a titration, and explain the function of acid-base indicators. So if you remember from before, we can analyze an acid or base by reacting it with a known concentration of the other. We have two types of titrations, strong acid, strong base, and weak acid, strong base. And just a reminder, the equivalence point is the amount, it occurs when the amount of titrant added is just enough to completely neutralize the analyte solution. So if we're looking at a strong acid, strong base titration, we have an initial low pH. So we only have strong acid present. And then as we add our base, we're slowly bringing that pH up until eventually we hit our equivalence point. So for instance, the reaction of hydrochloric acid and sodium hydroxide. If you remember when we reacted an acid and base, we make water, and a salt. The pH is going to go up slowly, and then you end up with a vertical curve. So if we have this guy, we have pH on the y-axis, and generally it's volume that we've added of base. Okay, so as we're adding sodium hydroxide, we notice that the pH is kind of slowly going up, and then all of a sudden we hit this point where it just skyrockets, and then it starts kind of evening out. So this vertical point, the midpoint of it, this is the equivalence point. So this is a pH of 7, okay, and that's right when everything has been neutralized. And after we go above the equivalence point, now the pH is all controlled by that excess sodium hydroxide. Now, in a weak acid, strong base titration, it's very similar to strong acid, strong base, but a little bit more complicated. You're still making water and a salt, though. And you start off with a low pH, but not as low as the strong acid titration. Okay, so again, we're starting with a little higher pH, and we gradual rise in pH as we add our base. It's going to do kind of the same thing until eventually it goes up very, very high. And just like before, the midpoint is the equivalence point. So, okay, so we have our pH here, and here's 8.72, our equivalence point for this system. So we're starting at a higher pH, slowly going up, and then starts going faster, 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 till eventually it goes really fast, and that midpoint of the vertical part of the curve gives us our equivalence point. Or just like before, now sodium hydroxide is controlling the pH. There's a much better drawing of what I tried to show, looking at strong acid on the left, weak acid on the right. And you can see that you can identify the equivalence point of both of those, that middle point of the vertical sections. But you can see the weak acid looks a little different. So let's go ahead and look at an example. We're looking at a titration for 25 milliliters of 0.1 molar hydrochloric acid, which is a strong acid with some strong base, and we want to calculate the pH at different volumes. And the first volume is at 0 milliliters. So at 0 milliliters, our pH is all HCl. So that means our pH here, the negative log of HCl, or of H3O plus, which is just equal to the concentration of HCl. So the negative log of 0.100. And so that's a pH of 1. Now for B, we've added 12.50 milliliters of base to the acid. And now you added less than a stoichiometric amount of base, so the base is all consumed. Okay, and we can tell this because if we look at 12.50 milliliter of base, and this times 1 liter per 1,000 milliliters, have 0.0, oops, sorry, my pen acted. 0.100 moles of sodium hydroxide per 1 liter. So let's punch this into the calculator. 12.5 divided by 1,000 times 0.1. We see that we have 0.00125 moles of NaOH. And the moles of HCl that we are titrating, we have 25 milliliters, 1 liter per 1,000 milliliters, and 0.100 moles of HCl per 1 liter. So we see units cancel. So we have 0.0025 moles of HCl that we are titrating. So in letter B, we've used up all of our base. We haven't used enough to consume all the acid. So now our concentration of our HCl is going to be equal. So we have 0.0025 moles minus 0.00125, because since all that OH minus is used up, the moles of OH is equal to the moles of H3O. And that's divided by our total volume, which is 0.0025 liters plus 0.012 liters, or 125 liters, sorry. And so this concentration of HCl, which is equal to our concentration of H3O, is 0.0333 molars. With pH is equal to the negative log of 0.0333. And so let's punch that in, 0.0333. That is equal to 1.48, or since it looks like we're doing 3 decimals, 1.478. Now for part C, since we added 25 milliliters of 0.100 molar sodium hydroxide, that means we've added the exact amount of moles of NaOH, same as HCl. So that means our pH is 7 because we have neutralized all the acid. We're right at the equivalence point. So we don't even need to do anything there. We can see our moles of acid are equal to our moles of base. Now part D, 37.50 milliliters. We can calculate how many moles of sodium hydroxide we have, just like we've done so far. So now we have 37.5. Might help if I typed in the right number. 37.5 divided by 1,000 times 0.1. We have 0.00375 moles of sodium hydroxide. So this is more than the acid, which means that the sodium hydroxide is now controlling the pH. So our concentration of NaOH is now going to be equal to these 0.00375 moles minus all of the hydrochloric acid has been used up. So that's that 0.0025 moles of it. And this is going to be divided by our total volume, which is 0.0375 milliliters plus 0.025, oh, I'm sorry, not milliliters, liters. We're just making these into liters. And so that gives us our OH minus concentration, which is 0.0200 molar. So since we have OH, we can calculate POH, which is the negative log of 0.0200. So let's type that in. And that is equal to 1.699. So our pH is equal to 14 minus 1.699. And then we get a pH of 12.301 or 12.30. So this is kind of a cool problem. You can then see how that pH is changing theoretically as we're adding more titrant. So now let's look at titration of a weak acid with a strong base. So we have 25 milliliters of acetic acid with a 0.100 molar acetic acid with 0.100 molar sodium hydroxide, and we're given the reaction. And we want to calculate our pH with different volumes of NaOH. So A, we are adding 0.00 milliliters. Okay, so that means here our pH is going to be using our typical ice diagram approach. We're just looking at the acetic acid by itself. There's no sodium hydroxide in here yet. So by doing a quick ice table, we have 0.100 molar. Hydroxide, we have 0. Oh, I'm sorry, we're actually not doing this reaction because now we're just doing this in water. CH3CO2H plus H2O giving us CH3CO2 minus plus H3O plus. All right, so approximately 0 hydronium, 0 acetate, no water, plus X, or minus X, plus X, plus X, 0.1 minus X, X, X. And then we know that the Ka of acetic acid is equal to 1.8 times 10 to the negative 5th molar. So we can go ahead and say that X is much less than 0.1. So this becomes 0. So Ka is equal to X times X over 0.1. Solving for X, which gives us our concentration of hydronium, we get 1.3 times 10 to the negative 3rd. So then our pH for A equals the negative log of that. And so our pH here is 2.87. So that is our pH for A. So A was the nice easy one. And now we're going to step it up with B, C, and D. Okay, so part B now wants us to titrate to find the pH when we add 25 milliliters of NaOH. So looking at the reaction, this now gives us the equivalence point, right? Because now we have 1-to-1 acid to base. So that means we've done all the acid, reacted it all away with the base. However, there is still weak conjugate base present in this reaction mixture. So the pH then has to be computed using the base ionization of acetate. So now we have a total volume of 25 milliliters from the start plus another 25. So we have 50 milliliters of our total volume. And then our moles of base that we now have are moles of the acetate ion. Is going to be equal to, we have 25 milliliters of sodium acetate, which milliliters, and we can use that as our acetate ion because there's one acetate ion for every mole of sodium acetate. So 1 liter per 1,000 milliliters. We have 0.100 moles of acetic acid for every 1 liter. And then looking at it, we have 1 mole of acetate ion for every 1 mole of acetic acid. So if we punch this in, we get that we have 0.0025 moles of the acetate ion present. So then our concentration now of the acetate ion, I'm just going to do this as A minus, is equal to 0.0025 moles for every 50 milliliters, which is equal to 0.05000 liters. And that gives us 0.05 molar solution of the acetate ion. So now, when this is acting as a base, we have the acetate CH3CO2 minus reacting with water, which is going to be acting as an acid here. Okay, because we've reacted all of our acetic acid is gone. So now water is acting as our acid. So now this is going to form CH3CO2H and OH minus. And the Kb here over this reaction is going to be equal to our H plus times OH. Well, yeah, we know that Kb is equal to Kw over Ka. And Kw is equal to H plus times OH over the Ka. And the Ka we looked up earlier is 1.8 times 10 to the negative 5th. And we know that Kw is 1.0 times 10 to the negative 14 over 1.8 times 10 to the negative 5th. So our Kb is equal to 5.6 times 10 to the negative 10th. So because of that, we can go ahead now and make an ice table for this reaction. No water. Now we're starting with 0.05 molar CH3CO2. And we are going to assume 0 acetic acid, approximately 0 hydroxide minus X plus X. So this is the standard ice table, X, 0.05 minus X. And we can go ahead based off of that KB and assume that X is much, much less than 0.05. So that becomes 0. So now I'm going to go ahead and erase this top stuff because I need more space. Okay, so now our KB is equal to X times X over 0.05. That's equal to 5.6 times 10 to the negative 10th power. And then solving for X, we get that that is equal to 5.3 times 10 to the negative 6th power. And that is equal to our hydroxide concentration. And so then we can get POH, the negative log of 5.3 times 10 to the negative 6. And this is 5.28. So then our pH equals 14 minus 5.28. So the pH then is equal to 8.72. So even though we neutralized the acetic acid, we still have that acetate ion that is still there reacting a bit. Okay, let's move on to part C. I'm sorry, these are so long. I honestly hate this type of stuff. I love titrations, but this part of it sucks. All right, so part C is 12.5 milliliters of NaOH that we want to look at. So this is half as much as we would need to neutralize all the acetic acid. So this is 1/2 the stoichiometric amount of titrant. So because of that, 1/2 the acetic acid has been neutralized, and this is going to give us the same amount of acetate. So if we look at the Henderson-Hasselbalch equation, pH is equal to pKa plus the log of base over acid. And here our amount of base is equal to our amount of acid. So that's the log of 1, which this becomes 0. So here our pH is equal to our pKa. Yes. Okay, so our pH is equal to our pKa, which then to find pKa, we need to take the negative log of Ka, which is the negative log of 1.8 times 10 to the negative 5th power. So then our pH here is equal to 4.74. All right, and then part D, we have 37.50 milliliters of sodium hydroxide. So here now we've reacted all of the acetic acid away. So sodium hydroxide is all that's left now to control the pH. We're not even worrying about the acetate ion either. So now that means that our OH concentration here is going to be equal to our moles of sodium hydroxide, which let's go ahead and calculate that really quick. 1 liter per 1,000 milliliters times 0.100 moles per 1 liter. So this is 0.003750 moles. So 0.003750 moles minus our moles of acetic acid, which you calculate the same way, and you get 0.00250 moles. We calculated that earlier, since that's all gone, and then divide that by our total volume in liters, which is 0.03750 liters plus 0.02500 liters. And that's 0.0625 liters. But when you punch all this into your calculator, then you get an OH concentration of 2.00 times 10 to the negative second molar. So now OH, oh, sorry, not OH, we want POH is going to equal the negative log of that. So let's punch that into our calculator. The log, so we get a POH of 1.70. So our pH equals 14 minus that. And that gives us 12.30 for our pH. Like I said with some of our earlier questions, I wouldn't give you all of these parts. I might ask you to do one part of this. I wouldn't make you do something like C, because even though I went through that very quick, it's not the most intuitive thing. So, yeah, I promise I'm not going to be super mean. I hate this stuff, so I don't expect you to be perfect at it, because I'm not. Okay, so let's talk about acid-base indicators. This is a nice change of pace. We add these to a sample that's being titrated, and these are really helpful for finding the equivalence point in a titration. And so the pH at which the indicator changes color is called the end point. And you want to make sure that you choose an indicator that has an endpoint that coincides with the pH at the equivalence point. So you need to make sure that you choose the right type of indicator, because there's a lot of them. Now, they are weak acids. So the weak acid is a different color than its conjugate base. For example, methyl orange, IN means indicator, in its acidic form is red. When you add it to an acid, it's red. But its conjugate base, so once you've reacted all that away to form its conjugate base, is yellow. And it has a Ka of 4.0 times 10 to the negative 4th. So again, different indicators have different color change intervals. Here's a nice chart showing you different color change intervals with different indicators. So sometimes you might be in the lab and you're doing this reaction, you have to choose the correct indicator. And it's very important that you choose the right one. There are some indicators that have two different color ranges, so they can be used for two different pH areas. But there's others that have very specific ones. Phenolphthalein tends to be very commonly used for some acid-base reactions. So here's some titration curves showing you indicators for a strong acid titration versus a weak acid titration. If you look at the red line, the bottom one, the titration of strong acid HCl, the blue litmus pH is pretty perfect for this. Even phenolphthalein is okay. All of these are somewhat okay, even though the pH isn't perfect. You still kind of get that vertical line there. to get that sharp color change. But when you look at the weak acid, its equivalence point is all the way up here at 8.72. Phenolphthalein is the only one that changes color in that area, in that pH range. So none of the other indicators would work because they wouldn't give you the proper color change. Okay, so that's it for chapter 14, but before I end this video, I want to go over the example that I skipped in our last section, which is example 15.10. And this was concentrations following precipitation. So in chapter 15.1, we were talking about selective precipitation and solubility products and KSPs. And this one we couldn't look at until we talked about acids and bases from chapter 14. So I wanted to go over it after chapter 14. So we're told that clothing washed in water that has a manganese concentration exceeding 0.1 milligram per liter may be stained by the manganese upon oxidation, but the amount of Mn2+ in the water can be decreased by adding a base to precipitate it as manganese hydroxide. And we want to know the pH required to keep the concentration equal to 1.8 times 10 to the negative 6th molar. So we first need to go ahead and write our equation and get our KSP, which we can look up. So the equation is MnOH2 at equilibrium with Mn2+ and 2OH minus. And this has a KSP of 2 times 10 to the negative 13. And if you remember, KSP, the solubility product, depends only on our products because our reactant here is a solid. It's not part of the equilibrium calculation. So we have the concentration of Mn2+ times OH minus to the second power. There's that 2 in front of OH. So now we can go ahead and solve for OH. So we know that OH minus squared is equal to KSP divided by our concentration of Mn2+. And so our concentration of OH is equal to the square root of KSP, which is 2 times 10 to the negative 13, divided by our concentration of manganese, which we're told 1.8 times 10 to the negative 6th. And so then we get that the concentration of hydroxide is 3.3 times 10 to the negative 4th molar. So we could have gotten this far last week, but it was what happens afterwards that I wanted to wait, because now we've got a concentration of OH, but last week we wouldn't, or not last, yeah, last week we wouldn't have known what to do with it. So now we can go ahead and use this to calculate POH. So POH is equal to the negative log of 3.3 times 10 to the negative 4th, which is equal to 3.48. And then pH is 14 minus POH, which is 3.48. So that calculates, let's see, that's a typo there. So we have 14 minus 3.48. We get a pH of 10.52. So we got to keep our pH at 10.52 to keep Mn2+ equal to 1.8 times 10 to the negative 6th molar.